5 fundamental principles that we're going to own. And once we own those, yeah, it's totally fun. It is totally fun. Okay? All right. So, picture on this is on page 20. The text will be on page 19. Here we go. Here's the cell, physiologist cell, protein on the inside. Proteins have negative charges in general. I'm sure Dr. Turco mentioned that. All right, here's the thing to remember. 4 electrolytes right here. We already know the concentration. What's the extracellular of sodium? What's the extracellular of sodium? 140. What's the intracellular? We don't know and we don't care. All right? We don't know and we don't care. But the point, the big point, is it's much, much lower than 140. Okay? It's much, much lower than 140. What's extracellular chloride? What's extracellular chloride? That's 104. That goes back to our BMP. 104, the rule of 4. Now, what's the concentration inside the cell? We don't know and we don't care. We don't know and we don't care, but it's a lot less than 104. What's the extracellular calcium? Well, we didn't even go through calcium. So, but the point is the inside is a whole lot less than the outside. The inside is a whole lot less than the outside. Now, put a little asterisk here because what we're talking about is free cytosolic calcium. All right, free cytosolic is very low. Now, we do have pockets where we have a lot of calcium. What are those called, those pockets that have calcium, have a whole lot of calcium inside a cell? What little organelle is that sitting in? Yeah, the sarcoplasmic reticulum has a lot of calcium. We're not talking about that calcium. We're talking about the free cytosolic calcium. It is very low compared to calcium outside. So notice, sodium, chloride, calcium, all much higher outside than inside. What's the extracellular concentration of potassium? 4, exactly, the law of 4. What's it on the inside? We don't know and we don't care. But it's a heck of a lot more than 4. So, potassium is the only one where we have a whole lot more inside the cell than outside. And it's very important that we understand this distribution. Sodium, chloride, calcium, much higher outside than inside. Potassium, much higher inside than outside. Okay? That is the framework we need to be able to start with, that fundamental framework. You don't have to know intracellular concentrations. Forget it. It's not important. It's totally unimportant. But you do need to know the concentration gradients. So there's a concentration gradient for sodium to diffuse in, chloride to diffuse in, calcium to diffuse in. That's the gradient. That doesn't mean they can, but the point is that's the gradient. Potassium, on the other hand, has a gradient, chemical gradient, concentration gradient to leave. This becomes important because one of the factors influencing the diffusion of ions is the concentration gradient. Simple diffusion. All right. What are my 5 fundamental principles? Number 1 is the concept, membrane potential. This is the separation of charge, electrical charge, measured in volts across the cell membrane. All right? Volts, separation of charge, creates a membrane potential, and the inside is negative compared to the outside. Reasonable number to work with is minus 70 millivolts. Okay, that's about normal for a nerve. All right. This is a separation of charge. It's the potential to do work. It's the potential to do work. It's just like an electrical outlet in your house, right? If you're in the United States, it's 120 volts. A lot of other countries, it's 240 volts. Stick your fingers on it. It'll work. It'll work. No, don't really. Don't really. Well, lick them and then stick them. Okay. No, don't do that. Don't do that either. You know, but I assure you it will work. But just trust me on it. Don't find out for yourself because it'll hurt. It'll hurt. It really will. That's all voltage means, potential to do work. So we have a membrane potential. A membrane potential, that just means separation of charge. Inside is going to be negative compared to outside at the resting state. All right. Second fundamental principle is electrochemical gradient. We already touched on this. Electrochemical combines the chemical gradient, concentration, and electrical gradient. Ions are going to move based upon chemical gradients, concentration gradients, and electrical attraction or repulsion. Now, all we have to remember for that is like charges repel, opposites attract. Okay, that's all you have to remember. Like charges repel, opposites attract. Okay, so let's look at this. If the inside of the cell is negative, sodium is positive. So electrically, do you agree sodium wants to move into the cell? Sodium, there's an electrical charge tending to pull it into the cell. Good. All right, for chloride, which way is it wanting to go electrically, in or out? Which way does chloride want to go electrically? Electrically, it wants to go out because it's a negative charge. Outside is positive, so that's the electrical force. Calcium, positive, wants to go in. Potassium, positive charge, wants to go in. So we have electrical forces and we have chemical forces. We call that the electrochemical gradient. All right, so we've got in our minds, we know the chemical gradients for these four ions, and we just remember electrostatic charges. Opposites attract. That's the foundation. Seriously, it'll be basically that easy. Watch. We'll work with it. I'll show you. All right, third is something called the equilibrium potential. This is huge. All right, this is huge. Look at the words. This is the membrane potential right here, membrane potential that puts an ion in electrochemical equilibrium. Electrochemical equilibrium, which means the membrane potential that results in no net diffusion of an ion. All right, now let's ponder on this one for a second, because this is a huge point. Equilibrium means no net change, right? Equilibrium. We all would love equilibrium. No change, no net change, just relaxed. All is good. Life is good. Nirvana, that works for me. You bet. It's all good. It's all good. Equilibrium. No USMLE questions. Yeah. So you'll get equilibrium after you take the test. Yeah, exactly. Exactly. All right. Now, remember, ions move based upon chemical and electrical gradients. Equilibrium potential is this number right here, that if the cell gets to this number, it puts an ion in electrochemical equilibrium. Now, be very careful with that phrase. This doesn't mean that there's no longer a concentration gradient. This doesn't mean there's no longer a concentration gradient. It just means that the chemical and electrical forces have balanced. So I may have a chemical drive in that's balanced by an electrical pull out. Follow? I may have a chemical drive in that's balanced by an electrical drive out. That creates an electrochemical equilibrium. Doesn't mean there's no longer a concentration gradient. It just means that a force in is balanced by a force out. The difference between membrane potential and equilibrium potential. Equilibrium potential refers to the ion. It refers to the specific ion. So each ion will have its own equilibrium potential. Each ion has its own. And guess what? You can calculate it. Nernst equation. Math! Yeah! Okay? So, the difference, membrane potential is whatever the membrane has. Okay? Whatever the membrane has. An ion will have its own equilibrium potential. And we'll show you the Nernst equation. You don't have to memorize the Nernst. You don't have to memorize it. You need to appreciate what the Nernst calculates. It calculates the equilibrium potential. Okay? It calculates the equilibrium potential. We'll show you the equation in just a moment. I woke your dad up? Oh man, now I'm embarrassed. Oh man. Sorry. I was just trying to wake you up, Miguel, not your dad. I guess I went a little overboard. So I'll go, math! Is that better? Math! Headphones, you got it. Something that's how it means. Okay? All right, so equilibrium potential means the membrane potential that puts an ion in electrochemical equilibrium. Each ion will have its own number, which means if the membrane potential gets to the number for the ion's at equilibrium, electrochemical equilibrium, won't move. You may have a force going in, it's balanced by the force going out. The forces are balancing each other. Okay? Now, when we get to some, I'll show you, we'll work with some numbers in a moment. If it's still a little fuzzy, that's okay. Hang with me. Just hang with me. Yes, even if the concentration is different, doesn't mean we lose the concentration gradient. I may have a concentration gradient in, but an electrical pull coming out. They balance each other out. That's the key. This is the secret. This is the inside secret to understanding how excitable tissue works. It's a secret. It's called the equilibrium potential calculated by the Nernst equation. Okay? Now, again, if it's a little fuzzy, that's okay. It's okay. We'll do many examples. But just for right now, appreciate each ion has its own equilibrium potential. And if the membrane potential gets to the ion's equilibrium potential, no net flux. No net flux. Okay? All right. It's okay if it's still a little fuzzy. Just hang with me. I totally understand. When we work through a few, all of a sudden you'll go, aha, I get it. Watch. Fourth is something called conductance. That's all right. Hang with me, Maria. You may be a little bit lost, but just hang with me. We'll work through. We're going to do lots. We're going to do lots of examples of this. Lots of examples. Right now, we're just laying the framework. Next is conductance. Conductance is the flow of an ion across the membrane. All right? Conduct. Think back to the idea of electricity conducting. Okay? Think back to the conduction of electricity. That means the flow of current. Same idea here. Conductance is the flow of ion. Ion's charged, so it's a current. and it will depend upon the permeability of the cell to the ion. All right. What's going to influence that permeability? We'll talk about in just a moment. Ion channels. Ion channels. Okay? All right. Fifth fundamental property is something called the driving force. Now, the driving force is the force working on the ion. The greater the driving force, if it can conduct, it will conduct. It is calculated as resting membrane potential minus equilibrium potential. Resting, we measure. Equilibrium potential will be calculated for each ion, Nernst. All right, let's sit back. I want you to look at that. Just think about it. Driving force is how far an ion is from equilibrium. Stop and think about that. It's resting membrane minus the equilibrium potential for the ion. So in other words, it's how far is resting membrane potential from equilibrium for the ion. Does everybody see that? Does that make sense? The further from equilibrium, the greater the net force. The further from equilibrium, the greater the net force on the ion, because it's resting minus whatever's equilibrium for the ion. So since I'm taking resting minus equilibrium, all I'm saying is the further from equilibrium, the greater the force to try to get to equilibrium. The further from equilibrium, the greater the force. Exactly. Each ion will have its own net force, its own driving force. Each little ion wants equilibrium. They're like selfish little buggers. They don't care about anybody else. They want equilibrium for themselves. I want equilibrium for me. I'm sodium. I want my equilibrium. Just like people. We want our equilibrium, right? Get out of my way. I want my equilibrium. Give me the equilibrium. I want to be happy. I want to be happy. Well, ions are the same way. I want to be happy. Happiness is equilibrium. So the further this cell is from equilibrium, the greater the force to want to get to equilibrium. Make sense? That makes sense? We'll get there, Nisbet. We'll get there. We'll get there. Membrane potential is just what we measure. Membrane potential is the potential difference across.